iCloud. Done. Hello.
Hi, so I'm just gonna be watching Sitting Part 2. I'm only like 15 minutes in, and it's 2 hours. I've just been working a lot, and then I closed tonight, so I'm gonna try to get what I can done right now.
Okay.
And I'm almost done with the 7.1, 7.2.
Sweet. Okay. Sounds good. Thanks for telling me that. Okay, what we are studying today and Wednesday is a confidence interval, which of course sounds complicated, but it's not. And I'm going to show you that. And in 9.1, the data is a percent. And so this is the whole ball of wax. And so here with me today, I have one of my favorite friends, the M&M. Not as favorite as a Snickers bar, but. And so what I want to determine from this sample of M&Ms is what percent of these are, let's see, which one should we pick? Unfortunately, they all taste the same. I don't know, let's do blue. So percent that are blue. And I would actually like you to determine this. You're too far away to touch them, but if I arrange them in a way that makes them countable, you should be able to answer what percent of these are blue. Notice how countable I am making them for you. I'm going to do this even easier like. Ooh, these smell good. I don't want to do math. I just want to eat them. M&Ms. Must have had too much coffee today. I feel jittery. So bust out your calcul machine and tell me what percent of these are blue. Am I right? Can you count that from where you are now? So this would be a sample of M&Ms, of course, because this is not all M&Ms. Compare with your neighbor. See that you didn't screw it up. Let's see, 5, 10, 15, 20, 25, 30, 35, 39. So 39 are not blue, and what is that, 12, 15 are? Is that right? Is that what you got? No, not 15, 12, 14. But you should not be dividing 14 by 39, because that is not the percent that are blue. Did you and your neighbor agree? I want to eat these or pass them out to be eaten, but I got to teach this class one more time, so guess I don't get to eat them yet. Bad news for you younger people that want to be healthy. Your craving for chocolate does not change as you age. Maybe that's good news. So percent Just lost one, so there'll be a different answer for next class. So, example, M&Ms. What we want to know is the percent that are blue. And so we got N, which is 39 plus 14, which is 40, 53. And X in this case, which is our variable, the number that we're blue is 14. So 14 divided by 53, did you get 26.4%?
Yes.
So what do I call that? Do I call that P? And I think I'm gonna, round that off. Do I call that P? The answer is no. What do I call that? Because if I say it's P, then what does that mean?
The population is not.
That means the entire population of all M&Ms in the world, which it is not, because it was just a sample. So how do I say that to people?
Yeah.
P hat. Now, what I've been alluding to in all of chapter 8 is the fact that this is not P. This is not the right answer for the actual population, right? Does it make sense? This sample that I took could be kind of a high percentage because I don't know if I like blue, I got lucky and got lots of extra blues, or it actually could be kind of low. Remember what we saw in the last section is the samples of these. If I had bags and bags and bags of M&Ms and gave one to everybody, and you all got, and I wish we kind of had time to do this. This is the kind of thing that I don't know, maybe we'll do in lab tomorrow or something like that. I'll think about that. But if we all had our own bag of M&Ms, we would not all get 26.4%. Does that make sense? However, if we graphed all of ours, some of you had higher, some of you probably would have higher percentages of that, some of you lower. You might even agree there's a chance if they were randomly distributed into the bag that you might not get any blues, you might get 0%. But does it make sense the distribution of all those individual samples, there's one of them, would be normal? That's chapter 8. And if we had enough of them, does it make sense we could actually determine P because P would actually be at the center of this? So just to kind of, I don't know, make your 8.1 logic. If this was the distribution of P hats plural, then we don't really know where 0.26 is in that. Is it at the center right here? Where P is in the real world, like if we actually knew the right answer to this question, by the way, we do know the right answer, I'll tell you that in a minute, but we don't really know where 0.264 is. Does it make sense? It could be a score way out here, really high percentage, way higher than normal, could be way lower than normal, or it could actually be lucky and it could be right at the middle of this. Does that make sense? That's chapter 8.1. So we just took a sample, just like you were going to do for your final project, and this is the best we got. If we're asking a question that no human has ever asked before, then there's no better answer than this one. If nobody's ever asked this question before, I have the best answer in the universe. But the problem is we don't know if it's right. You understand that? That's the key concept. So the question is, where does our particular P hat? Notice I said P hats plural. And so I'm not going to write this in here, but I could call this P1 for like our first proportion, our first sample proportion. And then we could have P2 and P3 and P4 and like a bunch of different samples. And so we don't know where this belongs. So it kind of makes no sense to put it anywhere. So what we're talking about today is the fact of something called the confidence interval, which is, this is our best answer as a substitute for the actual population proportion. But we don't want to just tell people, hey, they're 26% blue. That'd be kind of a crazy thing to publish. What would be cool is if you could publish 26.4, but then also add this idea of an error. And that's what we talked about on Thursday, this idea of, in your note sheet, an error. So I want you to have your note sheet out and stare at this. Like, how much error is there in our little study here? So let's just think about this for a second. This is interesting. I just forgot about this till right now, but are those p hats normally distributed? As I drew over here, does it actually look like that? There's a test for that. You remember what that is? Look at your note sheet. What's the test to see if these are normally distributed? You may remember I showed you different graphs that weren't, where the distribution wasn't normal. What do we have to check? Somebody blurt it out who thinks they know. Somebody that grew up on a chalkboard. We used to have a chalkboard, so that's really cool. Here's a hint. It's right there. Remember that? Again, I probably won't ask this on a test, but the thing, I want to go slow here because what we just did is kind of live. Like I opened up the bag and we just did it live. But remember, we know a lot of math about the normal distribution. And so if something's normally distributed, we have all this math that we can do, but it doesn't, we don't know anything if it's not normally distributed. So can you check that? Is this true? The shape of the distribution of p hats is normal if NPQ is greater than 10. Can you calculate NPQ? Do you know what NPQ is? You should. Well, we have a value for n. We have a value for p, and we know how to calculate q because it's 1 minus this. So if I take n, which is 53, times p, which is 0.264, times 1 minus that. And by the way, if you don't want to figure out what that is, you could just type 1 minus that in your calculator, but I think I'll write it down. What is that? 0.736. Showed you that the other day, and we're looking to see, is this bigger than 10? 0.264 times 0.736. Woo, that was close. We made it, barely. It's barely bigger than 10. Like we couldn't get it, almost couldn't get any closer than that. So we got kind of lucky, I guess you could say. I'm not sure what I would have done if that didn't work. So this is actually equal to approximately 10.3. So are the p hats normally distributed? Yeah, in other words, that's kind of cool. So what happened? You're all good? Okay. So how confident do we want to be that we're right here? In the real world, this is kind of determined by how important is the question at stake. I would say this is really low on the level of importance in life. If this was something like the health of your children, or should we put this person to the death penalty or behind bars for the rest of their life or something of that nature, that feels like, let's not be wrong. But it's like if we screw up the M&M thing, who cares? Who cares how many blue M&Ms are? It's not really going to change our lives, right? So let's say we want to be, I don't know, 92% confident. That seems a little high. This has to be something, at least as far as a math assignment, that we're told. In the real world, it would be something you choose. How confident do we want to be? We want to be 92% confident that the real p-value is kind of close to that. I'll show you what I mean by that in a second. Okay, so what we've got to calculate then is this error here. Notice the real p-value, which we don't know, we're hoping it's between our 0.264 plus the error and our 0.264 minus this error. So let's say the error was like 3%. Then we're going to take our 26% and add 3 and get 29%. We're going to take our 26%, subtract 3 and get 23%. And we're going to say we're 92% confident that the real P value out there in the universe, we're 92% confident it's somewhere between 23 and 29%. Does it make sense that we know our 26% is wrong? Well, most likely it's wrong. And so what we want to do is give some kind of a range. We want to give a range and say, well, we think the real answer is between here. So this error, we got to calculate this error. E-R-R-O-R, error. Your book sometime will call this a margin of error. Means the same thing. I think sometimes that's even abbreviated in your on your math assignment, like ME for margin of error. And notice we're told that's equal to this weird statement that we talked about a little bit the other day called the Z-score with this little weird symbol below it, and then multiplied by the standard deviation, which was the PQ divided by N formula that we already played with a little bit. And we don't know really P, so that's why the formula says P hat and Q hat, because we don't actually know what the real P is. We have no information about that. Maybe, and again, we'll never actually know. So the question is, what's this Zambridis right here? Well, that's based off that 92% that confidence. We want to be 92% confident. It's based off that 92%. So what is that 92%? Well, it's here. In other words, we're sort of splitting this off right here and saying this is the 92% here in the middle. Because remember, we know our 0.264 is not here. We're thinking maybe it's over here, maybe it's over there. We're not really sure. We're not really sure where our answer is relative to the right answer because we didn't perform. We opened one bag of M&Ms. We didn't open a whole bunch of them. And it wasn't even like the good size, right? The family size, the one you can barely lift. That's a side note, but like, why is fun size this big? I'm thinking fun size is this big. That makes no sense to me. 92%. Well, if this 92%, and I'll kind of highlight this here, when it says 92%, that's always talking about kind of the middle 92%. Would you agree it's, I don't know, not that typical if you have 92% to be out in these tails? Now, very important, what percent is in those tails? Blurt it out. 4% on each side. Does that make sense? So our error is actually 8%. So there's sort of an 8% chance we didn't land in there, but it has to get split in two. That's exactly what this means right here. We need the Z-score here that represents this location, but recognizing that we're splitting the tail into two parts. So we have an 8%, we're missing 8%, but we've got to put half of it here and half of it there. That's why this says half. So you've already done this. You've already been asked questions for this. Well, I'm going to give you a second to screw this up. Try it. Talk to your neighbor. Can you calculate what that Z-score is right there? What is that Z-score right there? How do you find that? Some of you are like, oh, I've been studying my rear end off. Bam, I'm on this. I'll be done in 2 seconds. Others of you are like, I did that. It takes a lot of practice to kind of own this stuff. This is hard. I would not say in one pass unless you were really studious. I bet a number of you are kind of going, I'm not sure. I might have known that at one time, but I don't know it now. So we know a lot about the normal distribution. The things we've done with this is normal CDF from chapter 8 and inverse normal. Which one is it? Which one is it? As in, let's hear it. It's okay to be wrong. We'll fix it if you're wrong. Go for it, Chelsea. Is that you talking?
Yes. The normal CDF.
Chelsea says normal CDF. Is she right or is she not right? Inverse. Let's see. Now we got both of them. Awesome. This isn't on this particular note sheet, it's on the previous one. But indeed, it is normal. It kind of is on this note sheet. What does inverse normal take in as an input? The area to the left. Don't we know the area to the left? Thanks to that picture I just drew. Do we know the upper and lower limit? In other words, do we know what these limits are right here? We don't know what those are, so we're not going to be able to type in normal CDF, but we do know the area to the left. So this is actually inverse normal. Thanks for being brave. I like it. So if I want to find that z-score, that is an inverse normal question. And so I've got to type in the area to the left of that. Notice that's 92% plus 4 more percent, 96%. Or I could say, well, the area to the right is 0.04, so then the area to the left is 0.96. And if all I need is a z-score for this, then I don't even need anything other than 0 and 1 for the mean and the standard deviation. Although if I wanted to go to the trouble to calculate those for this particular problem, I could. So inverse normal 0.9601. Again, most of your calculators don't have the ability to say that the tails to the left, you're stuck with that. So mine does. And so that tells me that z-score is 1.75. Which, by the way, means this one would be negative 1.75. Do you agree with that? Since it's symmetrical. This is a hard class. But again, if I asked you right now, I won't ask you, I'm asking rhetorically. I'm tempted to pick on you, but I don't think I will. If I was to ask you, what does that 1.75 mean? You should be able to answer that. It's not 2, so it's not unusual. That's not unusually high. But it's getting close. Now, make a note of this yourself, because your homework will ask you this. That value right there in your assignment is called a critical value. I hate terminology like this. So I'm going to kind of box it in. Like your assignment will say, what's the critical value? You know, and you'll go, oh, I don't even know what you're asking me.
The critical value is just z-score?
Yeah, it's just that z-score that we found. I'm going to rewrite it right here. Critical. So we found the z-score that represents the middle 92%. Cool. Notice the actual error though says take that and multiply it by the standard deviation. So let's calculate that. The standard deviation, I'm going to write SD right here, is equal to P times Q, our P value, the only one we know, not the real p-value, our p-hat value, because we don't know the real one. So p times q 0.736, all divided by n, which was 53. That's our standard deviation. My magic machine says second square root 0.264 times 0.736 divided by 53 is 0.06. I guess I'll call it 0.061. Double checking, did I type what I said I typed? Looks like everything's okay. Notice I said approximately 0.061. Now again, stop and think about what 0.061 means. That means, I think, that means that I have this value of this p-hat, this sample proportion that 26% are blue. And this should be powerful to you. Like, you do not understand this class and what standard deviation means unless you kind of go, oh, that's interesting. This is saying I could be off by 6%. As a matter of fact, it's typical to be off by 6%. Whoa. So that means 26% is not a very great answer. Does that make sense? It's like it could be off by 6%. So then what do I do to get this error? This E value. So let's see, I kind of had this, just to kind of make my notes a little clearer. I sort of had this calculation that I made and this calculation that I made. And now finally I can say E is equal to, well, as we said before, the Z value times the standard deviation value. So my Z value was 1.75, 1.75 standard deviations from the mean. I got excited. It's very exciting. Multiplied by the Z-score of this. Remember, that number is how many standard deviations you're off. So this is saying you could be off by 1 3/4 standard deviations. Well, the standard deviation is 0.06. If I multiply the standard deviation times the number of standard deviations, then that's going to tell me what my error is. So I take 0.061 times 1.75 and I get, oh, 10%, 0.107. Just writing myself a note. Whoa, I just did this study and I'm about ready to report to the world that the percent of blue M&Ms is 26%, but at a 92% confidence level, I have to kind of also say my study could have an error of 10%. Do you agree that's huge? That's gigantic. That's a lot of error. Oh my gosh. So kind of the conclusion then of this, my confidence interval, and again, stare at your note sheet here. My confidence interval is the real P that we don't know is basically within 10% of 26. 26 plus 10, 36%. 26 minus 10, 16%. So I'm sort of able to guarantee with 92% confidence that the real P is actually somewhere between 16 and 36%. That's a monstrous amount of error.
Did you say that you know what the actual P is for that?
Yeah, I do, and I'll tell you that in just a second. According to email some nerd wrote to M&M company, Mars. So what is my confidence interval? It is that P is less than my P hat, which is 0.264 plus my error of 0.107. Thank you. It's less than that amount, but it's greater than 0.264 minus 10%. So I'm just calculating this really quick, 0.264 minus 0.107. Which is actually rounded 16%. If I add them, I get 37.1%. Notice I said P there. So what does this really mean? I am 92% confident, thanks to the normal distribution, that I could just say P, but remember, sort of this is the real P, right? Mine's fake. Mine was a one random sample of one bag of M&Ms, which could have been totally weird, could have been out in the tails in this original distribution we talked about. We don't know where it is. I'm 92% confident that the real P is in this interval. And that isn't very telling, right? Like that isn't very satisfying. I would kind of like the error to be more like 1% or something like that. And then I would feel better than saying you have a 10% error. Oh man, that's terrible. So I'm not going to pull up this nerdy email, but according to Mars Company, the right answer to this question is actually 24%. They produce 24% blue M&Ms. Little side note. So now that we know that, does it make sense my little study wasn't too bad? Like I was only off by 2%. That's kind of cool. I won't take the time to bring up the email, but it's kind of interesting because whoever the nerd was that wrote back from M&M Mars Company said, we make them at 24% blue. And it even says they actually did like a whole test with people. What's your favorite color? What color M&Ms would you like? You know, those kind of questions, just like you might do for your final project, in order to basically find out, you know, what percent should they make of each one. You know, if everybody's like, oh, I hate orange. Orange tastes terrible, you know, and they chuckle to themselves thinking they all taste the same. But you know, it's like let's sell as much product as we can. So let's not make it weird, right? Let's make colors kind of match what people say they like, and then maybe we'll sell a few more bags as a result of that. But then of course they make them in that percentage, but then they get kind of all stirred up. Does it make sense? You could get a bag that's entirely blue M&Ms, or you could get a bag that has none. So they actually even qualified it saying, you know, we make them at 24%, but you know, there could be variation from that. Notice there was. It's only off by 2%. What's up? Nice and loud, what?
For the C-score part of like the error, like equation, how do you know which one to like choose? If you're finding two of these.
Yeah, in other words, I think I understand your question. How did I know to choose this one and not that one? Is that what you're asking? So watch what happens if I had chosen area to the left of 0.04. Same exact inverse normal, but instead of 0.96, I choose the 0.04. What do you notice about the z-score? It's actually the same answer. Like whether you call it positive or negative, it's actually 1.75. For that reason, you just answer the positive one. Actually, I'm not sure. Would my open math mark it wrong if you said negative 1.75? In the end, notice we're taking that number times down here, we're taking that number times our standard deviation. And so we're going to get, well, positive 10.7% is what I got. But if you use the negative, does it make sense? That's where this negative came from in a sense. It's almost like they use both. So that's a wonderful question.
So for like for confidence or critical value, that if you're given just a percentage, it's just how you wrote it, point, whatever the percentage is, 0 and 1.
Mm-hmm. Yeah, so to keep it simple, you can just let the mean and the standard deviation be 0 and 1 because you just need a z-score. And so notice we said we're 96%, we're 92% confident that the real answer to this question falls between 16 and 37%. And in most cases in life, we would never know, but in this case, we actually do know, and notice it did fall in between there, didn't it? Easily between there. You understand what I mean? Like in this case, we were lucky to actually be able to see how close our answer actually was to the right answer. But if you, in your final project, ask a question that no one knows the answer to, you'll never know. You see what I'm saying? If Mars did not answer this email, we didn't know the answer to that question, we just have to leave it at that. So we performed this study, and this isn't a very important study, therefore, if you only check with 57 M&Ms, then you should expect there's going to be a lot of error because you only check with 57 M&Ms. If this is really important, then why not check with thousands of M&Ms? Does it make sense that would actually help the error here? If we had thousands of M&Ms, does it make sense that here, when we divided by 53, we divided by 53, but just for the fun of it, even though it won't be fun, if I took 0.264 times 0.736, but I divided by, I don't know, 8,956 M&Ms, man, you got a lot of time on your hands to separate all those dudes out. Notice the percent we got. Did we get 6%? No, we got 0.4%. And when I take that times 1.75, notice my error now is only 0.08, which means I would have taken 0.264 plus 0.008 and 0.264 minus 0.008. And then I would have said, I'm 92% confident that the real answer to this falls between 25 and 27%. Does that feel better? Well, that's what, and if you don't check with very many people, you're gonna have a lot of error. If you check with 8,000 people, you're not gonna have near as much error. So occasionally you'll see something like this where someone will say the average number of blue M&Ms in a bag is 26%, but then they'll also say with an error of 10%. That's kind of a nice thing to be told because they're sort of admitting, hey, we did a study and we're not super sure how accurate that is. So there's a 10% error. All right, how's your brain? Are you taking that in? I don't mean, yeah, I got it, move on. I just mean, can you appreciate the value of that? Question.
I just had a question on the equation. So when you're looking at the error, that z-score symbol is always dA/2, and you treat it as a single symbol.
Yes, that's exactly right. So everybody understand that question? Garrett's question is really good. What the heck is that thing again? Couldn't that be interpreted as like z times that? But no, that's just a qualifier. Really, that's just z. It's just z for 92% is actually 0.96, not 0.92. So they're saying z qualified with the fact that you got to cut that error in half. That 8% error, we had to cut it in half. So this is just means a z-score. It's a great question. Now, I want to qualify this study. So let's say that, you know, what does this mean? What does this N mean? Again, I'm trying to give you one real, sort of real life example to kind of take this in. What? 10% error. I almost feel like this is a waste of time to even do this. This was terrible. To tell people there's somewhere between 16 and 37% that are blue, it's kind of like, thanks for nothing. I mean, that's ridiculous. 10% error. Brutal, terrible. What if you said, I want 1% error? 3 R's in error. That's actually, I'm gonna leave that. That's the perfect word to spell with 3 R's. I'm gonna leave it that way. And I couldn't even write R. It's embarrassing.
Wait, is that something? No, it's just 1%.
Yeah, it's 1%. That's another error. As I said, wouldn't that sort of feel better if I said, hey, I just did this study and there's only 1% error? That feels a lot better, doesn't it? Well, if you want 1% error, then the conclusion is, as I showed you a second ago, you need a larger value for n. If you want to have less error, you better go check with more people. Well, what n would that be? Take a look at your note sheet. What n would that be? If you take p times q times that z value that we just calculated a minute ago, 1.75, divided by the error, 1%. We want 1% error, and you square that. And in lab the other day, or in support class, we talked about how to remake this formula. If we resolved it for n, this is the formula we would get. Again, if you can do that, if you studied that enough that you're like, I can do that, there's a sense of confidence that I hope you have. It's like, that's kind of cool. Those aren't really different formulas. And I'm strong enough mentally to be able to make one from each other. That feels kind of good. Do you have to be able to do that to get your assignment questions right? No, that's why somebody did it for you. I don't think in the book they even show you how to do that algebraically. They just say, here's the new formula. And, you know, nobody would ever know. So n, we're told, is equal to p hat times q hat times that z score divided by our error, and that number gets squared. How are you doing in your algebra skills? If you plug all that stuff in, do you know what order of operations to do there? I see a multiplication, another multiplication, a division, a parenthesis, and an exponent. That's like all the order of operations there are. Remember, the order of operations is parentheses are first, then exponents are next, then multiplies and divides, and last adds and subtracts. I don't have any adds and subtracts, so I can ignore those. So if I plug everything in, then my p value that I found from my little experiment was 0.264, which means that my q value is 0.736. My z score was 1.75, and I would like an error of 0.01. This is the choice you're making. 10% is a terrible amount of error, so I want to redo this study with a better error. So, order of operations, what do I do first? Parentheses, there's only one thing to do in there. Do that. We've played enough with formulas in this class that you should know how to do this. And again, I only say that so that you think to yourself, hey, cool, I do. Or, wow, I haven't been studying hard enough, I'm behind. There's a lot going on in this class. Parentheses first, 1.75 divided by 0.01, big number. What's next? I've done parentheses, what's next? Exponents, I have one of those, squared, that number squared. Woo, that's a big number. Then multiplies and divides. So if I say times 0.264 times 0.736, bam. N is approximately 5950.56. In other words, don't open a bag with 53 M&Ms in it if you want to be accurate to 1%. Open a bag with 5,950. Now, interestingly, should I call that 59? Because you can't have 559.50.5 M&Ms, right? Little side note, I had this really nerdy friend in college who, I don't know why this just occurred to me, but he opens his bag of M&Ms and one of them is split in half. And he wrote a letter to the company talking about how embarrassed he was amongst all his friends at a party, and they sent him a new bag of M&Ms, which I thought was weird. His weirdness paid off. They should have said, "You're an idiot." If I want to be accurate to 1%, should I round that up, down, or off? Round it off, like to the closest answer. If you round that down, then your error is going to be slightly more than 1%. Does that make sense? Will it be irrelevantly close to 1%? Yes, it will. But if you actually want the error to be 0.01 or less, you're going to have to round it up. Even if this said 55950.1, you should call it 5951. If you want an error of 1%. Now, again, that's the kind of thing that you wouldn't get wrong on a test because the difference is pretty much irrelevant. It's going to be really close to 1%. But if you round it down, it's going to be a little over 1%. So that means you're not off by 1%, you're off by a little more. If you round it up, you'll be off by less than 1%. Well, like we saw a second ago, when I did it with 8,000 or whatever it was, I forgot what the answer was. Did I write it down anywhere? Notice that error was 0.008. Do you notice that's actually pretty close to 0.01? It's actually a little less. And why is it a little less? Because I did this with 8,956 M&Ms. So I got an error that was even less than 0.01. Did you notice that? That was just kind of random that happened. So technically, you want to round this up, not off, no matter what this says. In this case, you would have got lucky because you would have rounded that to 5951 because that's over 0.5. But if that said 0.1, you still round it up. So in other words, the idea is if you did it with that many M&Ms and you still got 0.264, 26.4% was your sample proportion that were blue, now you could report, my error is only 1%. That feels a little better, doesn't it? Now, as I hope you are beginning to think about your final project, does it make sense that whole string of calculations right there is kind of cool? That's the kind of thing, if your data you're collecting is a proportion, like this is one of the main things you want to be able to do in a class like this that's really practical in the real world. Now, just a little side note here. Did you notice we, I guess as it turns out, foolishly picked 53 M&Ms and we got this % from it, only to discover our error was so huge that we then said, I guess we'll have to redo the dumb experiment. So it'd be kind of like you asking 53 of your friends some question about COVID, let's say, and they report their answer, and then you realize my error is 10%. And now you're like, oh, how many people do I need to ask? And then you start over, except you have to ask 5,000 people that same question. Does it make sense? It'd be better actually to do this from the start. Like before you even run the experiment, if you say, I'd like to have 1% of error, then why don't you figure out n before you even go ask in the first place? Don't just start with a terrible answer like 53. What do you notice about this note sheet though? Right here. Use this formula if you know P and Q, but if you do not have a value for that, then just stick this number in there for it. In other words, you don't have a value. Now we did have a value for this 1.75. Remember that came from the fact that we chose a 92% confidence interval, and we have an error because we said we want the error to be 1%, but we don't have a value because we never even did the experiment yet. Pick 0.25. Where in the world did they get that? Let me just show you some examples. For those of you that like to know why. If you don't need to know why and your brain is full, then go la, 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 and don't listen for the next 60 seconds. What if my P hat was 0.7? Does it make sense then my Q would be 0.3? What if my P was 0.8? Then my Q would be 0.2. What if it was 0.6 and 0.4? What if it was 0.5 and 0.5? You see what's happening there? What they stuck in there was the worst value it could possibly be. 0.25, when you multiply those two together, is the worst answer you could possibly get. Notice it could actually be less, 0.21, or even 0.16, or 0.9 times 0.1. It could even be 0.09. But the worst answer you could possibly get is 0.25. So that's what they stuck in there, is the biggest answer you could possibly get, just to make sure to kind of be safe. So if you have a value like we did, it might save you some trouble. Just for the fun of it, if we did not have that value and we took 0.25 times our z-score divided by our error squared. Incidentally, notice I just typed the whole thing in there because your calculator knows the order of operations. We decided a second ago we had to check with 5,900 people, right? How many people do we have to check with if we don't know? Woo, that's expensive, man. That just cost you another 2,000. You got to check with 2,000 more M&Ms now because you didn't have kind of a prior guess. Let's see. How's your brain? Are you taking this in? So there was an M&M example. What I'd like to do is, let's do a second example. All I want to do is almost the same exact thing. Except for this time, I'm going to do cards. And again, this is just kind of cool because we can compare this to the right answer. So, I don't know, what shall we do? Now, again, in chapter 9.1, we're dealing with only data that's percentages. So I'm going to deal myself a bunch of cards, and I think I'll deal myself. Let's see, can I get you to see all of these cards at once? Yeah, I guess I could do that. I can get 12 of them on there. Now, what percent questions could you make up about this? I'm going to deal myself 12 cards, and I want to know what percent are, you tell me examples that I could make up here.
Clubs.
Clubs. What percent are clubs?
Red.
Red. What percent are kind of a color? What else? A specific number, like nines. Notice there's a lot more nines in there than you'd expect, right? Face cards. One face card. There's lots of things I could do. Let's pick something that's kind of unusual. Actually, like the number of nines here is pretty unusual, right? That's kind of high. So let's kind of take that. So what percent of my cards were nines? There's my sample. You should. And I want you to create a 90% confidence interval. Yeah, that's a good question. So this is just percent out of 12 cards dealt. I don't think I even need to know that there's 52 cards. Percent, I decided to ask the question, what percent, when somebody deals you a hand of 12 cards, what percent are nines? Now again, this is interesting because we actually know the real answer to this question. But again, we're just pretending that we don't. We're just pretending we asked 12 people. By the way, as a side note, I think NPQ here, because N is only 12, I think NPQ is not going to be bigger than 10, but we'll just ignore that for now. So you should have a sense that this was really unusual. So if you said, and by the way, what's the percentage? What percent of them are nines?
25.
25, 3 out of 12, right? You should have a sense that that's really high. That's kind of terrible, so to speak. That's very surprisingly high. But remember, we're pretending we sort of don't know. It's kind of like you just went and asked 12 people questions and 3 of them answered the weird answer that you happen. You believe in the Loch Ness Monster? And of the 12 people you asked, 3 of them like, heck yeah, I'm in on the Loch Ness Monster. You don't know it, but probably the population of percentage of people that believe in the Loch Ness Monster is probably not 25%. But you did your study with 12 people and that's the only answer you got. So the facts of the case are your sample percentage was 25%. And it's very important to note that you only checked with 12 people. Don't write this down, but 12 times 0.25 times 0.75. Notice that's not bigger than 10. So we can't really do this. We can't really do what we're doing right now. I need to deal more cards, so to speak. But that's okay. We're just playing anyway. So I want you to create a 90% confidence interval for your data. This was your data. Write that down because I'm going to put back up what I had for notes before so that you can kind of look at that. So you got this written down. I want to give you some time here, like to screw it up. What this should do is help you understand like what you don't understand. After we get the answer to this, then we'll take a little break because it's been an hour. So that's everything we just did. All you really need is the error. That's the issue. You got 25%. How much error is there in your study? You need a Z-score for 90% confidence interval. And you need the standard deviation. Talk to your neighbor or ask your questions and run around. I'd love to get for you to get this partially, if not completely, under your own power. This is the kind of question I'm going to put on the next test. I'm going to give you that kind of information and then say, go make a confidence interval. That 90%. So remember right here, we said 92% before, and then we stuck this into inverse normal to get the Z-score. Stare at that for a second.
I thought that the 90%
That was you deciding or somebody telling you, let's be 90% confident in our work here. Last time it was 92%. Yeah, it is not always 92%. That's exactly, that's exactly why we have different ones. So we pick that. So would you agree that so in the normal distribution, where is that? Not in the middle. This entire curve is 90%. These will have the longest lifespan, not very many percent. People are in here at the lowest. The rest of this is 90%. So these are the, in this case, it's talking about. Lowest 10% of the lifespan. Well, this is actually how much we use. Notice you're told that they have so on your note sheet, you know the percentage, the score that's inversed on that. Where's the inverse on that? So you can go area left, center, or right, but if you want area left, doesn't make sense. To me, because area left is- if you want 90%, that's the right. So then I can enter 10% deviation. Each other can respond. The mean in the center of this is actually 14. So you can think that's the average number of years that lasts. And 12, some smaller number than 14. So if your bulb burns out in less than 10 years, it's like yeah. No, that's not easy. Questions before I do this? Here's the, go ahead. Check with your neighbor if you got an answer. Go ahead. Looks good, I don't care. So, you can either do a Word document and bring Excel graphs into the Word document. It's probably a little easier to type in than Word. check with your neighbor.
Why did you try and eat that way, not this way? So I need that way.
We found it exactly this way. I just wrote the symbol for standard deviation. So we took the standard deviation times that z value right there, and that's how we got our error. It's the same.
So that's just a different way of writing the formula that's on our sheet.
Yeah, I did one thing out of laziness on our sheet. Isn't, just to add this to the notes, isn't this the standard deviation calculation? So down here, instead of writing that whole thing out again, I kind of got lazy and just wrote that instead. My laziness. All right, I'm doing it. This is what I would expect to see for notes. So our error is found by taking our z value, I won't be lazy this time, times our standard deviation. So I got to calculate those two things. So my z value. Since this time somebody only needed to be 90% confident, and notice that answer does change from problem to problem. Again, if this is you deciding it, it would be, how important is this question to you? How important is it that people believe in the Loch Ness Monster? If you wanted to be really sure, then you'd say, I want to be 99% accurate. If you're like, it's not that important, let's just make it 90%. I need this z-score right here, or the other one, as Melissa pointed out. What's the area to the left of that? Since there's 90% in the center, that leaves 5% in the tails. So the area left of that would be 95%. So if you say inverse normal, 0.95, 0, and 1, because all we need is the z-score, then I could just use 0 and 1 for the mean and the standard deviation. Inverse normal, 0.95, 0, 1. I got a z-score of 1.64. I didn't say anything about rounding, but on my open math, if it asked you to round to 2 decimal places, then you should not be rounding that to 2 decimal places. Do you understand that? You need to round it more. Don't round along the way. Round it more. I'd call that 1.64. So we might get a slightly different answer. So there's my z-score, one of my 2 ingredients for this recipe. Second, I need the standard deviation. P hat times Q hat divided by n square rooted. I need that. Again, I did this study ahead of time and got my P hat is 0.25. So that means Q would be 0.75, but I foolishly only asked 12 people. So I'm going to get a really large deviation, standard deviation, because I only asked 12 people. What is the square root of 0.25 times 0.75 divided by 12? It is 12.5%. Ooh, that's a big number. There, I have all the ingredients I need to find E now. So E, the error, is those 2 things multiplied together. 1.64 times 0.125. Okay, this is the first time you should say, whoa, an error of 20%. Wow, my study has an error of 20%. Ooh, that's terrible. You should have known that was going to happen, because you only asked 12 people. Now, for the sake of your MyOpenMath assignment, let me tell you all the ways this could be written. See if I can remember. See if I can remember what they're called. So what's your confidence interval? Here's one way to say it. Just say it's 0.25 plus or minus 0.205. Does it make sense that that would do it? In other words, add 0.205 to 25%, subtract 0.205 from 25%. I could just stop right there and say that's the confidence interval. Yep, that's one way to write it. Or you could actually do it. Do what that said. 0.25 plus 0.205. And this is probably what you did because that's what I did in my example earlier. So I got 0.455, 45% for the high end. When I subtract those two things, what do I get? 0.4? No, I don't trust myself. 0.045. Let's see, I don't remember what are these things called. This is a inequality form. That's writing it as an inequality. You have a couple of questions on your assignment right off the bat that ask you to write this confidence interval in a number of different ways. So there's inequality form. These are called inequality signs. They're not equal signs, they're unequal signs. Or there's another form called interval. Well, isn't this thing called a confidence interval? Confidence interval is actually just where you list both of those numbers. See, what I can't remember is if you put them in parentheses. You just list those two endpoints with either parentheses or sometimes brackets. That's actually interval notation. Do you see they're all saying the same thing? Do you agree those are all three saying the same thing?
So is, the first one, is that the, p hat plus or minus me?
Yeah. So this is like p hat plus or minus me. Remember, me is margin of error. So p hat plus or minus the margin of error. So there's like three different ways you could say this. As far as the test goes, I'm not going to say that. I'm just going to say, tell me your confidence interval. And if you gave me any of these three, I'd go high five, good job, who cares? They're all the same.
To clarify, did you say on the map, if it says to round, that we should round along the way?
Yes, but just if it says round your answer, like if it told us to round these answers to 3 decimal places, then you should be rounding at least to 4 the whole way until the very end. Again, on the test, I'm not going to say anything about rounding, just round it however the heck you want. And I can look at your work and kind of see that you understand the idea. But remember, my open math will be kind of a pain here because if it says round to 2 decimal places, then you're going to have to get it right to 2 decimal places. It also might say, it actually might tell you the form it wants it in, which I guess if it's a computer, wouldn't it have to? Like how it's not smart enough to look at this and say they're all the same thing. So it might say something like answer in this form, or answer as an interval, or answer as an inequality, or something like that. And you'll have to write it kind of the correct way, the way the computer wants it written. Be capable but annoyed. You're like, whatever. I don't like that way. Probably this is the best way. If I had to pick one, I'd say that, because notice it allows you to put P in here, which is the population proportion, the real proportion of people that believe in the Loch Ness Monster, based on your stupid little study with 12 people, is somewhere between 4 and 45%, because you only checked with 12 people. I mean, I kind of like that because it's got P in there. The real population proportion is somewhere in here. That's all the better you can, that's all the more confident you can be because you only checked with 12 people. Garrett, did you have a question?
No.
Andrew.
So like for our homework, it gives us interval form with percentages in it and wants us to write it in the p hat plus me form.
Yeah, so does it make sense? You know, I wrote this with decimals, but what if the little box had a percent sign after it? Then would you be able to say, you know, 25% plus or minus 20.5%? So even that, it's like, do they want me as write as a percentage or as a decimal? I got to pay attention to that on the assignment too. Again, you should be capable but annoyed. Like, whatever, I got it wrong. Like, I totally understood this, but.
Can you re-explain how you got those final values, the 0.45, between 0 and 0.45?
Yeah, so I took my error, basically my study found that 25% of people believed in the Loch Ness Monster, but I was disappointed to discover that I had an error of 20% in my study. So I took that 20%, that 25%, according to this on your note sheet, and I said the actual real population proportion of people that believe in the Loch Ness Monster are less than 0.25 plus 0.205 and greater than 0.25 minus 0.205. Like this is a sense the best. That's why I wrote the formula this way in here. Question.
Just ask that question a different way. So, how do you, so you, in the interval formula, you got 0.045. How do you get, and then 0.455? To write that in the p hat plus me, how do you convert, how do you get the p hat out of that? Put it,
In other words, if you're, are you looking at a homework assignment question where they give you this and ask you to write it in another form?
yeah.
Yeah, so there are some tricky questions that I would prefer you reason out on your own, but just to kind of do this as an example. Like, what if you were told the, and again, I can't kind of consider, I'm going to make this easy, but I'll kind of consider this, well, there's no reason to make it easy. Let's make it a little bit challenging. So if that was your interval, in other words, the real percentage of people that believe in the Loch Ness Monster is between 20 and 64%. That's a great way to say that. The right answer to this question in the real world, I'm 90% confident is somewhere between here. But what if somebody wanted you to rewrite that in this form? How would you get p hat? Well, does it make sense p hat is in the middle of these? How are you going to figure out what number is in the middle of those? What's right between 20 and 64%? Take the average. In other words, 0.2 plus 0.64 divided by 2. .42. So 0.42 would be right in the middle between 0.2 and 0.64. That would have to be the middle. Notice it wasn't, that's one of the disadvantages of this form, is that you don't know what your original study was. So now I can say that p hat is 0.42. I know that that's right in the center. Well, if that's the case, then how much error is there? How far do you got to go from 0.42 to make it to 0.64? And how far do you got to go from 0.42 to make it down to 0.2? Well, the error or the margin of error would be how far do I got to go from 0.64 to get down to 0.42? The answer is 0.22. So another way to say the same thing would be 0.42 plus or minus 0.22. Even if you had to guess and check your way for a while to get those two values, eventually you could do it. Now I'm checking my work. If I took 0.42 plus 0.22, do I get that upper end? Oh, I do. If I take 0.42 minus 0.22, do I get that lower end of 0.2? Oh yeah, I do. So cool. I rewrote it in another form. Again, not something I'm going to ask on the test. Okay, let's take a break. I don't have anything new I have to teach you. Look, we just have to be able to be good at this. I want to ask you another slightly different problem, but we've been sitting here a while, so stretch your legs. Ask me questions about homework or whatever else you want, though. just learned from Samantha's question, like it asked her to answer an interval notation, it wants those parentheses around it. If it doesn't, hers was marked wrong, she put the two numbers like that, 0.2, comma 0.64, but you didn't put any parentheses around it, then she added them, and then it's right. That's annoying, but it wants those parentheses. Learn something. So we will be changing this to this new time. And so what do you type in there? So I think you do this. That's gotta be a whole number, 'cause you can't check what 2080 is like. So then you got, that's in there. So that's what I was wrong. So I was looking at before. So your decimal is decimal. You can check. Okay. But because then it's number of people you're gonna have, is reasons why you can't get it. No, I'm just. I think because we're near the end of this class, I'm probably not gonna be doing. Problems. There's a chance I'm not sure. Basically, today is the beginning of percentage. questions?
What should I do with my car?
Do something with code. What's that? Gee, that's fine. Yeah, I can move Other than the school making me wear a mask,
Because I have kids, I don't want to have something.
well, get some, if they get it.
Yeah. Pretty sure I had it. In the beginning.
Perhaps if they have that, nobody says they're using a case.
Yeah, I was out for like 2 days today. And I got a bunch of people in my micro classes, I was taking it on for home. And the instructor was like, she actually flew this scout. And at first was like, what was your thing? When the coach was coming and said, she came back and telling the story. And I figured it out. Like 2 months later, when they started telling us, and I bet the kids are. And, you know, everybody knows. But you moved and I never got the answer yet, so I don't know.
I wanted to tell you that, I didn't realize that I could have sent you things correctly. And I didn't set up my actual, because I've been trying to. The other modular, the margin now, because of opening attachments, so I was going to need, and I didn't want to just work it out. So I'm gonna figure out.
Yeah.
Yeah, I know, it's just not really like that.
You sure can.
For the final project, I kind of wanted to do like successful feedback, like how,
Feedbacks?
yeah, like vaginal birth after cesarean.
Oh, okay. That's a
And
great idea.
I was gonna do it kind of like, tell me your age and if it was successful or not. But then, at what point, like if someone is like, well, I've had 4 or I've had 3, then you just kind of like, I feel like if you don't include that data, then it would be like, but you get what I'm saying? I'm like, I don't know. Kind of, so just in it, I don't want to like disregard that data, because I feel like that's important, but then,
Well, and it would seem like,
and I'd have to have the age variable in there, right?
yeah.
Like
Well,
how old were you when
yeah, and
you
that's
had
exactly
a
what I mean, because it's,
failure or
well,
success?
you could choose to or not to. If you did choose to, does it make sense if you kind of chapter 4 where you have age as compared to the success rate, so to speak, because you can't, because you have 2 sets of data now, you see what I mean?
Mhm. So what?
So you
like,
could
how would
choose to ignore that and just say, I don't know, what's the percent of women, not, and just ignore that. And I mean, it's kind of like now, because this one thing happens with you. It's like, oh, this person died from COVID, but they never say, you know, what were their other,
Comorbidity.
exactly, what were their other comorbidities? You know the answer.
I got
You know
into
that,
nursing
so-
program. I was so excited.
Ooh,
I
okay.
found out last week. That's why I'm kind of like correlating.
Yeah. Because there are other issues, and so it's like, you know, the percent of people that didn't have a successful cesarean could be related to age. And so, you know, again, it could be, oh, I didn't think about that, or I'm actually intent to deceive. It feels to me like intent to deceive because they don't,
they never report on their extenuating circumstances. in
I
those
just didn't know if
deaths,
there'd
and
be
so-
enough data if they just had failures and successes, like, is that gonna be enough to work off of?
I would just keep it simple. In
And
other
just
words,
do-
Just recognize because I don't want you to have to work ridiculously hard at this. Just get a bunch of data and then just report if I wanted to do this better. Maybe I only ask, for their very first one and don't ask about second, third, fourth. Because
Oh, that would be a good
maybe the
idea.
second, third,
Okay,
fourth
like on your
play
first
into the
try,
first one.
was it
Yeah,
successful or
exactly.
failed? Okay, no, that's.
How are you gonna get that out? Are you gonna
I'm
ask?
part of the, because I had to be back with my second son, and so I'm part of like a
Oh, okay, sweet.
support group. So I was just gonna make a post
Yeah,
in there,
yeah.
and there's a lot of members in it.
Okay,
so-
that's a super idea.
But then again, I was thinking like, is that gonna be like persuaded towards one or the other? Because if someone didn't have a successful one, they probably aren't hanging out in that group anymore, type of a thing.
But again, that's another example, like, I'm super glad that you noticed that, because that's exactly, like, you could draw all these conclusions and the whole foundation of your study is totally wrong, because who are you asking? You're asking the wrong people. It's like going
Yeah.
to an AA meeting and asking people about alcohol. It's like,
Yeah, the people that
You're-
had
you're not-
failure
you're not
are
getting a
most likely
random
not gonna be the
sample,
ones
so-
showing up.
the important thing is just to crunch some numbers on this project.
Okay, I was just like, I
But
think.
that's a
I'm thinking
wonderful
too hard,
question. If
but
there's, no, I mean, if you want your study to actually be of any value,
I'm
you
just
can't
honestly
gloss
curious.
over, you can't gloss over that at
Yeah.
all. So you really want to ask kind of a random sample if you possibly can. But again, what would it mean to do that? Like, if the answer to that question is, my life is ruined because now I don't know how I'm gonna collect the data, I mean, that kind of thing. But that's what I'm saying, if there was money involved and there was, more than just curiosity about something, that you might have to take this to some other level. Possibly you could get that data from a hospital.
I don't know if they would release that
Well,
info.
without names though, they might.
Yeah,
It'd be worth the try.
they're really against it, but
Right,
they want low risk, they want,
yeah.
so.
Whatever you do though, just note the shortcomings.
Okay.
I'm doing something wrong from so 310 people asked if they like dogs, 95% said yes, asking for 99%. So from what I understood, doing this is how you got your margin of error. The z-score times.
The
say
Z-score for 99%. You said 99%. The Z-score for 99% is not that.
do- I did it for 95.
That's what's wrong.
Okay.
And that's not even 95, because 95, if it was a 95% confidence interval, that's half in each tail. Like-
Right.
Like this right here, when we did 92%, I did not put 92% in, I put 96% in.
Right, because of the 0.04.
Exactly, because of the 0.04. So you gotta do the same thing. Even if it was 95%, you don't put 95 in there. You
Right.
Put 97.5 in there.
Yeah.
So think about that. Just,
Okay.
keep looking at it until we get it. Okay, let's just do a couple other somewhat practical examples, and should have plenty of time to turn you loose to maybe work on your, what time is it? 12:07. To maybe work on your assignment or whatever else. But let's just, again, make up some kind of example questions. Let's see, what shall we do? So let's kind of make this like your project. So you have this question in your mind. Let's stick on the example that we talked about earlier. You're interested in the percent of people who believe in Bigfoot. Do you believe in Bigfoot? Man, when I was a kid, I won't go down this rabbit trail too far, but that was when Bigfoot was hot, man. That was right when that dude
had the big shoes on, was running around in the forest, making all the marks and all that stuff. And then I went to I don't know if it was like a conference, but some dude had plaster molds of all the feet from some local place, and they were on display, and everybody was looking at it. I'm like, oh wow, look at that. And everybody's talking about how many pounds it would have to weigh to make the indention that deep and all that stuff. Okay, so you decide you're going to figure out what percent of people, this is your final project. I want to know what percent of people in the world believe in Bigfoot. Remember, I said in the world, but does it have to be in the world? Could it be in the Rogue Valley? Could it be at RCC? It doesn't have to be the world. The population could just be in your family. You could actually know the population percent because you asked every single person in your family, because that's what you care about. You don't care about the whole world. You only care about some smaller version. So let's limit it to the Northwest, since this is where Bigfoot really lives, right? Northern California, Oregon, and Washington. So you're going to perform, but instead of just going out and asking randomly 12 people, let's do what this says and calculate how many people we should ask before we even start. So we do not have a value. We did not go perform even the most rudimentary. We didn't ask even just tiny 12 people. We have no idea. So let's find N first. And we decide we want to be really confident. We want to be 99% confident. I don't know if this makes sense to you, but if you want to be really confident, does that make sense? You're going to have a really big error. If you say, I don't really care how confident I am, 60% is good enough, well, then you're actually going to get a smaller error. But we want to be 99% confident we're right, that we actually have the correct percentage in Oregon. If you want to be really confident, that's going to cause a large error. Notice the ingredients for our formula here. We don't have values for P and Q. We have 0.25, but notice our recipe calls for two things we don't know. We need a Z-score and an error. What kind of an error do you think we should have? Notice this has to be given, and let's say we're happy with a 2% error this time. So notice I just literally told you E, the error is 2%. We can just stick that right in. But I did not tell you Z, you got to figure that out yourself. So as we did before, you go find Z. So you put in 99% and you get this answer. But I screwed up. What's wrong with what I did there? That is not the Z-score for 99% confidence. Where's the 99% again? Remember, you got to cut the error in half. Think about the picture. I am saying the middle 99%. How much does that leave in the tails? 1%. But you got to split that in half. 1%, 0.01 split in half. Notice you can't do it in your head quite so easy this time. There's only 0.005. And so armed with that, what should I have typed in then? 0.995 or 0.005. Just understand you're going to get a negative answer for that, but either one works. So I'm just going to go back up to what I typed before. And again, I want to show you both of these really quick. 0.995 gives you that answer. 0.005 gives you the same answer, just negative. They're both true. But it makes more sense to have a kind of a positive error. So you usually give the positive one.
But notice again, I have a rounding choice here, and you got to pay close attention because again, your homework, your online homework could mark you wrong because of rounding. And so, you know, what do I call that? Well, if the MyOpenMath gave you permission to round this to 2 decimal places, what should you call that? 2.58. If it did not, then I'd leave it a little further out just to be sure. So I don't know. I'm gonna make it 3 decimal places. I have no good reason for that. 2.5758. So that'd be 576. So I can now find n. I have all the ingredients I need. I have my z and my e, which were given. And so now I can go find n. N is equal to 0.25 since I don't have a prior estimate times that z-score divided by that error squared. So this is cool because now I'm about to learn how many people I'm going to have to go ask. And again, if you have access to some social media account, maybe this isn't going to be terrible to ask this question. But if I have to walk person to person on the street saying, do you believe in Bigfoot, and make record of what they say, I'm sure hoping this isn't too big of a number if I have to do that to gather the data. 0.25 times 2.5576 divided by 0.02 squared. Woo! That's bad news, friends. I'm not going to do this now. Like, I'm not going to go ask that many people. I do it if I have Facebook access or something. But what is the answer that MyOpenMath is going to want for this? Can you ask 4,147.36 people a question? No, people are discrete. It has to be a whole number. What do we say about rounding? Up. That will make your error slightly less than 2%, probably 0.01997 or something like that. It'll be slightly less because you ask slightly more people. But as I said, if you want a good answer for error, if you really want to know the answer to this question, you're going to need to ask a lot of people. Now, in the real world, would it be wrong to go online and Google what % of people believe in Bigfoot? Does it make sense? You might find an answer to that question, in which case this number could actually go down if you found that online somewhere and you said, oh, I guess I'll use that. But of course, you're wondering, like, you don't even know who did the study, whether they, you know, who did they ask? Did they ask people at a Bigfoot meeting or something like that? It's like, how did they get their data? So you're not inclined to trust it. Remember, for your study to be good, you've got to ask random people. I don't know what random people are, but you got to be careful not to ask people that are in a group that either might not believe at all or, you know, really believe or something like that. Just for the heck of it, I wonder what would have happened if what did we say a second ago? Didn't we decide this would have been 5.8 a second ago? Is that what we decided? What if we had rounded that to 2.58? Do you think that's going to make a big difference? Notice it kind of did, because then the answer would have been 4161. Now it's in the same vicinity in terms of the number of people you ask. But again, I'm a little worried about this because of MyOpenMath. You know, I hope it says I want you to round that z-score to 2 decimal places, because it means I'm going to get it wrong. And am I wrong? I mean, both of these answers are correct. You understand that? And as a matter of fact, if I rounded to 3 places, but what if I'd have left all the numbers in there? I mean, if I'd have left all the numbers in there, it would have been even better. So that was actually 575829, 575829, 575829. Notice that's actually the best answer, 4147. That's actually the best answer. That's the right answer. But you see how, like, rounding along the way is kind of an issue? So man, I hope they tell you how they want you to round that, or tell you not to round at all, or something like that. I did see one question, because I was looking, James had a question, and it did actually say, it's cool to round this to 2 places, but it didn't actually say you should. It just said it's fine if you want to, but if you chose not to, is it sophisticated enough to know that 4148 is actually right, but so is 4161? I doubt it. I mean, how would it do that? I'm a little worried about that. But again, that's one of those things where you send me an email and say, I got this right. The question wasn't worded good, or maybe you just didn't read carefully. Maybe they were trying to tell you how they wanted you to round so you get the dumb answer right, but that's going to be a problem, right? It's not going to be a problem on the test, because I'm just going to look and see what you wrote down. I'm going to see and look what you wrote down right there, and then I'm going to know if your answer makes sense. Oh yeah, they totally understood this. I'm not going to care.
So you're not sure how they want you to round one.
The one that I looked at with James, because it said it's okay to round to 2 decimal places, but actually what they meant is you better round to 2 decimal. You better round the z-score.
Oh,
The
okay,
z-score, and again, they're not calling it a z-score, they're calling it what?
critical.
A critical value. So it says in there as a side note, it's okay to round the critical value to 2 decimal places. So as a side note, I'll just add this to my notes, but as a side note, 0.25 times 2.58 divided by 0.02 squared actually came out to be 4161. Now, in the real world, does it make sense? I mean, you're asking 4,100 people, your error is going to be close to 2%. It's not perfectly 2%. Who cares? It's around 2%. I mean, that's fine. You're close enough. So don't lose any sleep over this. But I'd be very interested if you, as you leave this class, that this is one of the big takeaways, because this is, as I said, what your final project looks like, in the sense that you're about to perform some kind of a study in the real world. Notice you can actually do that now. That's kind of cool to think you know exactly how many people to ask. And then as a result of your study, you can report on the answer, but you can also report on the error. So I'll ask you just one last question. So now you do your study. We'll say with n equals 4148. You chose that one. Yep. So you go do your study and you find that, I don't know, 57 people believe. I believe. You have that bumper sticker on your car? I believe. I don't know what it is. It's like Bigfoot gets getting in everything. You notice like his pictures everywhere. I don't get it. So, but notice, remember, you don't get you don't ask a question and get a percentage. You ask people, do you believe, do you not believe? You ask 4,148 people, most of them said no, but 57 of them said yes. So now you can make your percent. The key is just, you got to know where percents come from. Again, I just want to give you a second. Can you create your confidence interval now? I haven't changed anything. We still said we wanted to be, we still said we wanted a 99%, we wanted to be 99% confident. And we know our error is around 2% because of the number of people we asked, but I'd like you to go recalculate your error and notice that it actually is. It actually is right around 2%, just like we thought. as an estimate, because you already know your error is around 2%, does it make sense? You could actually do this problem really quickly. Just think about that. But again, I'm just going to give you a couple of minutes to think about this. Again, this is an interesting question because in order to find the confidence interval, we need to know the error. So when I divided 57 by 4148, I got, and again, I'm rounding how I choose to, but I got 0.0137. I'm going to call it 0.014. So in other words, I already know that that's 0.014, but don't I already know the error is 2%? Like, didn't I design n so that the error would be 2%? Like in one sense, I don't even have to recalculate all this. Now, we'll check that in just a second, but something kind of interesting happens here. So listing it, and again, ask yourself the question, what is this called? This is inequality notation. Go ahead.
Like say that.
Yeah, like what is, yeah, I will. Yeah, I will. That's a good question.
Dumb it down for me.
Interestingly, when you go 0.014 minus 0.02, you actually get a negative number, which actually I guess is not really possible. I'll go ahead and write it that way. Remember, it would have been just fine to say 0.014 plus or minus 2%. Like those are both good ways to say that. But again, what does that actually mean? It means that your study found that 1.4% of people believe in Bigfoot, but that's your study, your p-hat study, and therefore you know it's wrong. But you go on to say that with 99% confident, I'm 99% confident that the actual population proportion of people that believe in Bigfoot is somewhere between 3 and 0%. Again, that's satisfying to me in the sense that, like, I don't know for sure, but I did check with 4,000 people, which took me a lot of time, and I'm really mad about that still. But as a result of all that work, I can say that the actual population proportion of people that believe is between 0 and 3%. That's tight enough that I feel like that was worth the effort. I feel like I know something now, right? If the error had been 20%, it's kind of like, oh, I got 1% and the error is 20%. Somewhere between 0 and 21% of people believe, and I feel like I don't know that much.
Did you put that answer into limit as 0 or?
Yeah, good question. I think they're sort of careful to make up something that doesn't say that. In other words, Yeah, should I put 0 here? Because you can't really get a negative, or I'd probably put this just because it's probably formulaic and wants
So it
to,
would be on the graph, right? So
yeah,
you could
and because,
plan
yeah,
out-
on the normal distribution, it would show up on the graph, negatives show up there, so I would say it'd be better to put that in there. But I don't think that'll happen in my open math, the little that I checked. Just for the heck of it, let's calculate that error really quick and see if it actually was. See if it really was 2% like we said. So I'm just gonna, use that error formula right there and say, okay, well, what's the z-score? We already calculated this. But let's do it again really quick. We already calculated the z-score for 0.995. And I'm reminding myself, oh yeah, there it was. There's that z-score. And then we have to multiply that by the standard deviation, which was P of 0.014 times, notice like I'm too dumb to figure out in my head what that is. So I'm just gonna be lazy and say, well, whatever 1 minus 0.014 is, that's Q. You don't have to figure it out, just type in the formula for it. Divided by, I asked, what do we say, 4148? I asked 4,148 people. Actually, I'm gonna do something. No, that's okay. I'm gonna leave it there. What do I get for an error? Hey, look at that. Oh, actually, don't look at that. That's way less than 2%. I thought it was gonna be like right at 2%. I did. So I'm like, now I'm suddenly thinking, what? Why did that happen? Anybody know why? I just figured it out, but anybody know why that happened? Remember, to start this off, we used worst case scenario here because we didn't have an answer for P and Q. Whereas when I just plugged this in, now I did, because I went and asked a bunch of people. So I actually had a value for P and Q, and it was nowhere near 0.25. And so I got an error way less than that. Basically, I asked too many people. I asked way too many people, I guess you could say, because I just had to assume that, well, maybe it's 50-50. Maybe 50% believe and 50 don't believe. And so in this case, remember that number 0.25, if I took 0.014 multiplied by 1 minus 0.014, do I get 0.25 for that? No, they're so far from being 0.5 times 0.5, I get a really tiny number there instead of 0.25. And so as it turns out, if I'd taken that times my z-score, which was 5.7 something or other, 5.75 was it? Didn't I even write that down anywhere? There it is. No, 2.58. 2.58 divided by my error squared. Notice if I'd had that estimate ahead of time, I would have only had to ask 229 people. Woo, that would have saved me some time. I wish I'd went on the internet to see approximately how many people believed, because I had no approximation and the percent happened to be so small. I ended up asking way more people than I needed to. Ooh, and because I asked so many people, notice I got an error that was way less than 2%. Where did it go? I think it was that one. It was way less than 2% as a result of that. It was like half of 1% because I asked so many people. Interesting. Okay. I'm not exactly sure what we'll do in support class tomorrow, but I would say off the top of my head, like we're too far into this class to still be practicing fractions and percentages and all that. It's kind of too late. You either got that, you're doing okay, or you didn't and you're dying now. I think would be the best use of time off the top of my head for you to like do tonight's assignment tonight, so that we could start off the first part of the class and let you ask more questions, clarifying questions about this, like why did you miss something in my open math? And hopefully we'll be able to determine it was just some stupid rounding mistake versus there's something profound that you didn't understand. And probably what I would do is go around the room as opposed to, collectively answering. I'd rather answer your particular question. And then maybe we'll kick off what's going on Wednesday, which is the same thing, fortunately, except for the data this time is not going to be a percentage. It's just going to be a number. In other words, I'm interested in this rope and I'm going to pull on it and see what its tensile strength is. How hard do I have to pull on this rope before it snaps in half? Which maybe doesn't matter, except for what if I'm hanging from that rope because this is a rescue situation and I'd like to, sort of be sure it's not going to snap and kill me. So now our data is, how many pounds does it hold? The average is 2,127. Like our data is a number, not a percentage. And then we got to do the same thing.
I don't
So
know if I'd be calculating that if I was hanging by a rope.
should do that ahead of time. Let's take this class first and then we'll go hang from ropes. That should be the final for this class. Like you design the rope and then we'll hang you off a cliff. And if you don't break, then you pass.
I don't think I would be able to handle
It's like,
it.
put your money where your mouth is, man. Let's do this. Okay, stay after. You're welcome to work on your assignment or get out of here because we sat here too long.
Which is code for.
Yeah. Just, so this is kind of. Confidence stuff. So these work from the confidence level. And then you get the feedback from. Yeah. Then, stating the parameter of interest, where do you get that?
The parameter of interest is basically the percentage. What we're interested in here is a percentage. So
Like, what? So are they talking about like the p-hat percentage? So interested in.
does it make sense? It doesn't make any sense to report 397.
Right.
Yeah, put these bottles in 397 and we'll line it correctly. That means nothing. That's not any foot.
So interested in value 18.3%. Confidence interval in context.
It's kind of cool here that they put the parentheses in the comment and body, so they just have to type in two numbers.
Right.
For the upper and the lower bound. Right, but again, it's like, okay, good, we found that.
Well, in this case right here, we said, we're confident, we're 99% confident that the real value for the percentage of people who believe in Bigfoot is somewhere between here and here. It's between 0 and 3.5%.
Okay.
We only performed a study. Right there.
Yeah, I got the same question as yours, I just got almost. But I got more questions too.
Yeah, so that's annoying. It's the same question you just asked. That's not worded very well because it didn't say error, they said standard error. which
Right.
actually means standard deviation.
Got it.
Okay.
Okay. Okay. Perfect.
I still got some questions.
Yeah.
What exactly is it asking for? What's the state?
Yeah, that's a complicated statement as well. But it's basically like, what is it we're trying to figure out? A second ago, what I was interested in is the percent of people that believe in Bigfoot. Study and I found that, well, it sounds like about 1% of people believe in Bigfoot.
What was out when I was looking at it?
Yeah. Well, it's, I mean, you're actually answering that before you even do this. You're actually answering that based on,
Yeah.
what is this person interested in? What do they want to know? What is it that they want to hear? That's what the law is. It's correct. What is this person want to know?
This one, somehow I got started on.
Tell me if that doesn't fix it, and we'll look deeper, but I think, as I was saying, you just got excited, of course you did, it's just statistics, you're gonna get excited, right?
Yeah, no, that's good. Sorry, instead of dividing by 200 people.
I'm doing the numbers now. But then I tried.
The problem here is. The problem is 2.9%. That is not 2.9.